Hi, it's Sadaq and my name is Akhraf Muhammad Sadaq and my student ID is SWE2502284. And in today's operating system second assignment video, I've already implemented and solved the deadlock problem in dining philosopher's problem using semaphores. So now let's dig into the problem, the fix, the problem itself, the causes, and let's see the two versions of the code running. Yeah. So now let's move to the setup. So here you can see it is my diagram of my problem. 5 philosophers sit at a round table and there are 5 forks between each pair of neighbors. To eat, a philosopher needs both forks next to them, like the left one and the right one, uh, to eat. Each fork can only be held by one philosopher at a time, so it's naturally modeled as a binary semaphore. Value 1 means fork is free, and value 0 means someone is holding it. Each philosopher actually picks up a left fork first and then reaches for the right one. That sounds fine, but it's exactly what causes the problem I'm about to show you. This is not a simple race condition, it's a deadlock. In 1971, Kaufman, Alfik, and Shoshani showed that deadlock needs 4 conditions to hold at once. So, as you can see in the slides, they are mutual exclusion, hold and wait, no preemption, and circular wait. So my naive design satisfies all 4. Each fork is exclusive to one holder. A philosopher holds their left fork while waiting for the right one. Forks can't be forcibly taken away, and this is the fatal one. If every philosopher grabs the left one first, you get a closed circular chain of waiting because everyone is waiting for someone, and that causes the problem. This diagram here shows it clearly. Philosopher 0 here waits for philosopher 1's fork. Philosopher 1 waits for philosopher 2's fork, and so on all the way around back to the philosopher 0. It's a complete cycle. Nobody can move forward because everybody is holding one fork and waiting for another that will never be released. That's a deadlock. That's a pure deadlock. So to fix it, I only need to break 1 out of 4 that conditions. So I choose circular wait. So my idea is add 1 extra counting semaphore, call it the room semaphore. Initialize it to n minus 1, so 4, not 5. Which means there will be 4 philosophers that are going to take 5 forks, not 5. One will be waiting. This means at most 4 philosophers are ever allowed to even attempt picking up forks at the same time. Since there are 5 forks and only 4 competitors, by pigeonhole principle, at least one philosopher is always guaranteed to get both forks, eat and release them. The fixed version adds exactly 3 things. The first thing is the semaphore declaration, the sem-t room, like we declare it, and then we initialize it, and then we call it before a philosopher touches any fork with a matching fork. Let's say after they put both forks down. Same fork logic, same 1 second delays that caused for the deadlock before. Now they are going to be harmless because the room semaphore never lets a full cycle to be formed. And we hope and we believe and we know that it's gonna solve our problem. So let's see it alive. The first thing that I'm gonna do is here I'm gonna run the broken version. I ran it, and you can all see 5 philosophers they're thinking now, and then all 5 picking up their left fork, and now it's nothing. It's frozen. Which means it is a deadlock. So now I need to press the Ctrl+C and stop the program, and now let's run the fixed version. Now the fixed version, and watch. So yeah, thinking, then it's picking up forks. Now you see the eating message appearing for each philosopher. It runs all the way through, and at the end, it prints all philosophers have eaten, no deadlock, and exists on its own, not like Control C like we did a couple of seconds ago. So same thing, same timing. The only difference is that one extra semaphore. So to summarize, the unsynchronized version satisfies all four Kaufman conditions and deadlocks every single run. The fixed version breaks circular weight with a single counting semaphore, and every philosopher it successfully. This shows the core lesson of process synchronization. Mutual exclusion alone isn't enough. So you need to make sure the conditions for the deadlock can never all hold at once. So yeah, that was the thing that I wanted to talk today. Thanks for watching and thanks for your attention.